My name is Ali Rahim. I'm Professor of Architecture and Director of the MSD Advanced Architecture Design Program at the Weitzman School of Design at the University of Pennsylvania. The AAD program is hosting a series of talks titled Building Experts by practitioners and educators whose design work and buildings serve as exemplary in the discipline of architecture. There are 6 talks in total, including today, and are held on Fridays at 9 a.m. or 9 p.m. Eastern Standard Time. They're delivered by 3 Western and 3 Eastern architects. Each presenter has been asked to describe one building from concept to built form in 45 minutes, to be followed by questions and answers. The talks are by Preston Scott Cohen and Carl Dorkin, of Preston Scott Cohen Inc. and Harvard University, Nader Tehrani, NADAAA and Dean of Cooper Union, Patrick Schumacher of Zaha Hadid Architects and Director of the AADRL, Shui Guo, Chair of Tsinghua University, also Dean of the Tsinghua University in Shenzhen, Rosanna Hu, Neri and Hu Architects in Shanghai, and Zhu Pei of Zhu Pei Architects in Beijing and Dean of China Academy of Fine Arts. We're very excited to bring these experts together to share their experiences and expertise with our students. I couldn't be more pleased to have Preston Scott Cohen and Carl Dorkin, the principals of Preston Scott Cohen Inc., an internationally renowned architecture firm in Cambridge, Massachusetts, to kick off the series. I have known Scott for a very long time, but what's impressed me the most is that he has been very interested, and the firm has been very interested for its deployment of unusual geometries and for its original approach to integrating new buildings with the urban and natural environments. To become an expert, I really would study Cohen's trajectory. I think it's exemplary with regards to how he shifted from the academy to practice. His practice originated with experimental projects, the most important of which was his entry for the I-beam competition in New York and Taurus House, both of which I vividly remember from the late 1990s. This set the stage for another period of work. During the 2000s, it culminated in several major built works during 2010s, including the Tel Aviv Museum of Art, a Mir building, the Goldman Sachs Arcade in New York City, and the Taiwan Museum of Art in China. Since joining the firm in 2011, Dorkin has collaborated with Cohen on the projects for the Tobin College at the University of Michigan, the Sarmiento Performing Arts Center in Bogota, the Bet Shalom Synagogue in Overland Park, Kansas, Hefei Science Museum, Xining City Center, and numerous other projects. Cohen is author of Lightfall, The Return of Nature, and Contested Symmetries, which is recognized for having established pedagogical strategies that combine typological analysis and studies in projective and other types of geometry. That has really what's motivated his project for his entire career. He has authored numerous theoretical and historical essays, 2 of which come to mind immediately. Toroidal Architecture, that was published in a special issue of Architectural Design, AD, that I edited, titled Contemporary Techniques in Architecture, and Elegance, Attenuation, Geometry, published in Elegance, also a special issue of Architectural Design that I edited with Hina Jamel. In addition, his work has been widely published and exhibited and is held in numerous museum collections internationally. Awards and honors include first prizes in 8 international architectural competitions around the world. Cohen's induction as an academician at the National Academy of Art, the award in architecture from American Academy of Arts and Letters, and 5 Progressive Architecture Awards. It's a phenomenal trajectory, right? Academic work, developing your own project. We talk about this a lot through the program, and then moving the theoretical and explorative project of design into built work. And I think that's the recipe of becoming a superlative architect in the future. Cohen is currently the Gerald McHugh Professor at Harvard University Graduate School of Design, where he was also the chair from 2008 to 2013, following a deep history and phenomenal lineage of chairs at Harvard. Scott and Carl will speak to us about their project for Performing Arts Center about to begin construction in Bogota. Please join me in welcoming Preston Scott Cohen and Carl Dworkin. So I'll let you take over now, Scott. All yours.
Okay. Well, thank you so much. I'm going to begin, and Carl will join in shortly. But I just wanted to say that this is really extraordinary opportunity. I love the idea of focusing on a single building with such intensity. That's a very Ali way to do something. And, you know, he really is rare in that he wants to go so deeply into these questions of construction, talking about a model of practice that emerged from experimentation. He would know what that means. I really would love to have the opportunity to meet all of you in the context of his studio. I know that must be a great pleasure. Well, let me jump right in. The way we like to work is to problematize, as we put it, form in architecture, and in ways that will do very specific things, very specific, exciting things, we hope. Today, we're going to tell a story about hyperboloids. Now, this is part of a much larger story. Many projects have these in our office, but this is specifically geared toward this one project. As Ali, you talked about, this is that the Performing Arts Center in Bogota. We are highlighting here one element in it, which is this extraordinary stair, this double stair. And you will see that what happens with these stairs is that they enliven this building. They make it theatrical even before you enter from the piazza. One for going up, one for coming down, or they are, let's say, the ends of a curtain about to open or shut. There are many possible metaphors, which I actually think are meaningful. They resonate in a way, but it is also just pure geometry. If we were to look now at why we did this, we start with this big theater. It's 2,100 seats. And you will see when we show you, we also have a very large black box theater, that in this process of creating this facade, which turns out to undulate, to respond to that corner of the two cylinders, and we'll come back to this, what you will find is that these two stairs have created a sequence for dealing with a very difficult site situation. Let me tell you about the site. Basically, we have a seriously compressed situation. It's far too small. It was incorrectly planned. It was not anticipated that there would be building such a large performing center there. It's right across from this enormous development that OMA have begun, master planned. And as I said, a site too small. So we began with the problem of taking this program, which is very cumbersome with many elements, including a gallery. And as I said, well, it also, besides having a black box and the 2,100 seat theater, it has many other parts and facilities for rehearsals. It has VIP, lounge. It has so many things, and you can see them here. But these two on the right with the red dashed line around them, that's the really tough part. A large lobby and circulation space that is everywhere in the building. So we began. We got this site, and here is this theater, but it really barely fits within the setback, as you can see. And we struggled with this for a long time with consultants, there seemed to be no way to make this work efficiently and to have a reasonable lobby. The lobby was so tight and small and planned. So we thought, why don't we make it a ring? A lobby that's a ring all the way around the theater. This didn't go over well in terms of circulation, in terms of the congregating of crowds. Can't do it. Eventually, as you move through this, you will see what happens. We begin to push things up from below the theater to relieve space in the plan. And in this process, we evacuate space for a lobby on the ground level. It's very interesting because as we worked through the project, it kept lifting because more and more of the back of house had to go below the theater. And it was still trying to connect to things that are underground, which was causing a lot of this back of house to kind of violate the theater, to travel through the theater, like toroidal, almost toroidally, Ali, toroidal space. It was passing through and down into another space below. The back of house was for quite some time doing that. Finally, we just lift the whole thing off the ground. We convinced them. We found it's a long process to arrive to, but eventually the theater is out of the ground entirely. We have an orchestra pit under it, so it's even lifted higher because of that. And it's really up there, and we get a huge lobby. You can see the lobby here in section in the model. So now, let's just look quickly at the plan. See that big lobby there that you come into a little bit, swirls on the floor. They're activating a series of processions, processions up and down and in all kinds of ways toward ticketing, etc. You can see the orchestra pit is right there behind the lobby. As you rise through, you are going to see that we have a very exciting arrival to the lobby on the level of the seating. And you see the two stairs in the corner there. These two have become a means to kind of create a very dramatic and exciting inward-facing sequence of passage on up into the balcony level and beyond it to these other spaces like the black box up there on the upper left. Anyway, it's a very intense interior, very packed, very, very tightly, incredibly tightly. Carl is juggling the program, compressing it, and even parameterize the quantities, the areas to get them in there. The section is, as you can see, expressive of that compactness. Okay, let's pass through these quickly because we've got a lot to show you. And I'm going to turn this over now to Carl to tell you about how the geometry came about.
Okay, so hello everyone. I want to return briefly to the notion of the 5 projects, and I'm going to start with the basic geometric construction for all of these projects in this narrative that we are working on. And this involves a sequence of hyperboloids strung together tangently, and the surfaces are trimmed to include only a portion of the full hyperboloid. So here you can see the construction sequence of each hyperboloid adding to the next one. And there's a lot of constraint in the way these surfaces link together. And throughout all of our projects, our goal is to produce surface continuity, but also to make manifest that constraint and tension. So to create a tense and taut object where the tension in the geometry is visible and apparent. And we're always asking ourselves whether you can see the tension that was actually within the piecewise continuous stitching of all these surfaces. So here you can see them superimposed on top of each other. So that is the underlying geometry for the facade and for this whole project, and I'm going to explain that in detail. And here in this video, you can see a property of the surface, which is called the skew angle. Can you see that video, everyone?
It's not running. That's too bad. I have to go to the next slide.
Okay, you can see, so let's return to the geometry. So In this particular version of the project, we begin with this pretty little piece of geometry where you have two hyperboloids that share a constant line of contact for different skew angles. So this is the basic principle for the geometric construction that I just showed you. However, in addition to this piecewise continuous stitching of trimmed parts, it's possible to leave the whole hyperboloid to create this beautiful double condition. And this is the start of the geometric exploration for the pack. And you can change the proportion of these things together. Making the proportion weird is always a good idea. Scott is never content with the straight up proportion. And you can nest multiple ones together so they can share multiple different skew angles. And you can stack them on top of each other, which produces this line there that you can see. And you can try different permutations of that. So this is a common thing, this particular construction, but what people don't often realize about it is that this line of intersection can be thickened to make a space. So you can add a gap between the two hyperboloids on the line. And this is the moment of innovation for this project, because the implications of this gap are sort of profound. So here you can see various versions of the gap. And I really hope you can see my video here. You cannot. Anyway, this is that particular thing. And you can see that actually it's possible to elaborate that gap into an incredibly complicated involuted space. So this is sort of where we tried to go based on that innovation. But actually, we sort of stepped back from that moment and left that for a later exploration. And we took this particular diagram where you have these two hyperboloids, and this became sort of profound for us because it allowed circulation back and forth between these two halves. And so we thought, what if we could add a stair to this? And so we became interested in putting spiraling stairs of changing radius inside of these two paired hyperboloids. So here it is back to the condition without the gap. And here we are adding stairs. You can see this is one volumetrically distinct stair clinging on to another volume that would have a stair within it. And we worked on various versions of this. And here we are beginning to add the gap back in. The gap makes possible sort of cross-contamination between the stairs. And these are the concept diagrams for this. This is a diagram of a single layer of interweaving, interconnected stairs that are nested inside of two hyperboloids. And the final diagram of that idea. So the gap leads to this. And then we started again playing around with changing the proportion, which again is always wonderful. We didn't stop. There are other sort of wilder possibilities. And one of the things that Scott always pushes us on is to try some of these rather than staying on the pure diagrammatic version. And these other versions are less pure, but they're possibly more interesting. And that's something that I've always really valued. So here's one with a surface with a stair nested inside of it. It's a fascinating direction for a project that we didn't do someday.
That one needs to get done.
Yes,
like
it does.
We will do it.
And here's the inside of that. Look at this one. Here's a stair clinging onto a surface, like a barnacle. And these are, again, other possibilities for projects that we didn't do based on the same underlying idea. This is a tiny stair hanging onto a surface and sort of spewing out and becoming part of the landscape. Here are two stairs wrapped around two interior hyperboloids. It's a stair attached to reeds or straws. And each one of these nested hyperboloids has a moment of tangency with the others, so along a single line. So you can imagine those relationships changing as one grows or shrinks. You can visualize them stirring around. This notion of motion and the fact that something is never stuck is something that, Scott has constantly drilling into us. So I would love to continue with this idea also, Scott. It's a really good one. And here's one spiraling out from within a surface, becoming part of the surface, merging with it. Here's another one pushing into a surface, a stair falling out of a building, and the possibility of an inside one and an outside one in this, nested, implicated dynamic. It's another one.
Let me just say one thing about the stair, Carl.
Go for it.
The goal from the beginning was to deal with this problem of the building that's too full of the theater. The theater was absolutely filling it, and there was a very, very limited area for a lobby adjacent to it. It would have to be the second lobby, not the one below the theater. So when you move up into the building to actually, prepare to enter the theater itself, this becomes one of the most important aspects of the whole experience. The Stair of Garnier in Paris is absolutely profoundly the most important part of the theater. So this stair is the realization of an effort to make an extraordinary experience moving up through it. Now, why is it in this contorted form? It is relieved toward the bottom, owing to the way the theater operates in section. We also thought and so it's tightening as it moves up. But we also wanted to have people experience, while moving in it, the fact that sectionally the building is, let's say, not simply an extrusion. Theaters don't extrude as normal other buildings do. As you know, they're very sculpted forms. And this facade is both trying to address itself to the plaza, present this drama of the stair, and have the stair be experienced inside in such a way that you're aware of the movement of the form of the building. Now, the idea of it be a tight duality, two things so tightly bound together, was somehow the beginning and the end of the story. The curtain that wraps around the whole building and shuts or opens here, this is the point of commencement and conclusion to the whole building. That ending, that beginning, the stair up, the stair back down. This duality seemed absolutely essential to us. So it's all of those things. A duality, an expression of all these pressures. You see what I'm trying to, and we want to do it in a very, very geometrically disciplined way to express all of that. It's very hard to make a stair happen in these hyperboloids this way. This is okay.
Yeah,
that helps to explain
that is
why
definitely the case, because otherwise we're just talking about tilted stairs with how
no,
do we
have
get
to
there?
Explain what our main
Yes.
motive, what we were
Why
desirous.
we do it at all?
Yeah, what we were desirous of. And in each project, there are these kinds of desires, these kinds of needs for certain things to happen formally, we feel.
So we also had been exploring tilted stairs in some of our other projects, which you can see here. So we had this sort of trajectory we were working on. And the idea of a tilted stair is actually kind of hard to realize, as Scott was saying, because in order to be code, you can't have a migrating spiral stair with changing radiuses. Each segment of the stair has to be a true spiral for its height, like a series of cylinders nested that shift within a larger shape. And I wish you could see my animation because it makes it clear, but each one of these cylinders will shift off of each other, and the error, the flex between the spiral is taken up in the landing. And then what we do is we add a smoothing step where these railings tie together the buffer. And you can see we have extra space in the stair so that the path that you walk on is a circle. And then when you get to the landing, there's enough space for you to shift. And overall, they produce something tilted. So here's the diagram of that shifting sequence of stairs.
So yeah, so the stair is broken by having broken into these pieces in order to conform to, it can't smoothly occupy this tilted cylinder. Carl, you haven't explained that we ended up when deploying this in 2 tilted cylinders.
Yes, I have not. That comes later in the narrative. This just
We'll
talking
wait.
about the stair. So this is the final stair in the project. And here you can see the completed stair in the model. We have to start somewhere. So, we're not showing you the facade, but we'll get there. This diagram, actually, this column is too big. It's kind of fascinating. This column that was holding up the stair is filling up the whole stair. So that had to become a super post-tension column, which you can see here. They had to make it skinny. So this, you're now looking at the Revit model of the stairs, the final Revit model of the piece of the stair. This is all happening concurrently with the facade development that we will get back to. That's the Revit model. So we have this glass guardrail. We have these handrails that are offset. And these are the plans of the stair migrating in space. And one other thing to note, Scott was talking about how these stairs, they have to come up from, they're part of the ceremonial sequence that is respondent from the fact that we have a lobby that is below the theater. So everyone has to move on them. So they're enormous. And so actually this stair is 10 meters in diameter, which is that big in the size of the room that you can currently see me in. This is our office. And that's the size of the stair. So there's also a basement, but the stair isn't in the basement.
We've used our office many times to measure and test light. That skylight there is how we figured out the Michigan skylights. And now the size of this. The fact
we had no idea how big this was until we. Oh no, it's enormous. And that obviously, these on the right-hand side are the stress diagrams for that stair. So this giant thing needs to be structured. And one thing that Scott never allows is putting stairs on hanging cords. It's like putting a stair on crutches. And so this is the model we were sending back and forth to the structural engineer. And the railing is a giant beam operating with the thickness of the stair to hold it up. It's a giant curving beam. All right, so now we're going to go back to the facades. Again, you remember that construction of hyperboloids. This is the basic tangency condition. However, we were not interested in this pure version of one surface being attached to the other. We tried many other less pure options, as I noted before. So we started attaching hyperboloids that would hold these stairs to the building with belts. That's our first idea. And then we made more belts with circulation inside of them. They could be galleries or lobbies. Remember those sections Scott showed at the beginning with the lifted belt? So these things are happening concurrently, right? 2 belts squeezing the form out, making a canopy. This belt is a strap pressing into the facade. So something interesting to note is you can see this belt is not fully articulated. It becomes tangent to the surface. And that also is a property of hyperboloids. They can be merged or split by virtue of splitting the isocurves. And that process looks like this. You can have a single hyperboloid that splits. So, this notion of the belt merging with the surface, can be traced back to the geometry. And you can make objects that look like that by the splitting. So here you can see the behavior deployed again with the stair. This stair has a negative and a positive relationship to the facade. And here again, the stair falling out and the canopy spewing out into the lobby, into the site. And then we tried these super intense connectivity diagrams. So these are spheres, hyperboloids, and hypars all interconnected into these complicated objects. They're all different. All these different types of surfaces can have tangencies with each other, and they can hold together and start to break apart. You can see there's these spheres sort of caught within the surface of the project. And the one on the right is the first one where it sort of starts to appear like a curtain. And then the superconductivity diagram led to this notion of the anamorph. This is a particular one that we wanted to do. It's another project we haven't done yet that we would like to do. And this is a video of it, which you won't be able to see, but maybe I can click through. You can see the anamorph distorting in this superconductivity diagram of the spheres and hyperboloids sort of inverting. And one thing about it that's fascinating is you can distort it, you can twist it, you can shear it, you can scale it, and it retains its property, its ability to be panelized into flat surfaces. So it can become this incredibly distorted, twisted object while still maintaining its intrinsic properties. You know, so wonderful. I was like, we did it, Scott. And he was like, we got more ideas. So everything is always churning and going forward. So we tried this one and I was like, you can't make me do this. It's ridiculous. It looks
Terrible.
humorous, but don't laugh because this is the one that becomes the final one. So it's getting a little more tame. It's got this nose. It looks like a rhino. Getting less bizarre.
Oh, you're making it sound like one thing led to another. This is not exactly what happened. And we had another problem, everybody. There were people breathing down our necks and not liking a lot of this. So let's also remind everyone that we're not the only ones making these decisions about which direction we should go in.
That's right. We're like, should we
began
show
to
this?
like certain things more than others. Well, and that may not be what we would have done.
That's right. So we ended up with 3 that we thought we could accept, and we presented those 3 to the client. So those 3 are the ramp belt, the anamorph, and the curtain.
Of course, there's that.
And we let the client choose. So what did they choose? They chose the curtain, which at this point, now our goal becomes to make this buildable. So in order to do that, we have to build it affordably, which means we have to get the number of panels of the facade down to a small number that can be mass produced. And we have to interrogate whether those panels can be curved or whether they need to be flat. But the problem is we ran out of time, as Scott was indicating on this scheme, and this is the only one of all of them that is not panelizable. It's just a loft, a screwy loft of 2 surfaces together, and we said we'll figure it out later. So we have this totally messy thing. Nothing is flat. Nothing is repeated. Every panel is unique. Every panel is doubly curved. You know, but this is what the client wanted. So that's what it's going to look like.
Never have shown him this. But he wasn't liking the other things. We became desperate.
Right. Then we turned the building around, you know. Scott is always questioning things. Now the building's facing the other way. So I want to tell you a little bit for your information about panelizing hyperboloids. So this is the geometric part of this talk. So you can panelize a hyperboloid into flat panels with any what's called conjugate curve network. So in the case of hyperboloids, the conjugate curve network we usually use is this one with mirrored ruling lines. So that's a flat panel in the middle. And you can proliferate panels around. It should be noted that when you have these partially trimmed surfaces, it becomes difficult to get the panels to end in the right places, and that can have a problematic effect. You can try different grains of fineness, different scales of panelization, which we always do. Another thing that is beautiful to point out is that you can panelize with cones, like that. Those are cones that intersect, which is sort of beautiful, honestly. It's kind of wonderful. Just something to be aware of. And another fascinating thing is that you can panelize along the other direction, the other side of the conjugate curve network, with cylinders. So those are segments of enormous cylinders, and you can intersect them, and that produces a panelization. And you know, as those approach infinity, it returns to the original hyperboloid. So that is how panelization works. Sometimes, though, we trim these asymmetrically. So the orange ones here are symmetrical hyperboloids, trimmed with the saddle in the middle, the skinny part. And they have less panels because they have mirrored identical panels around the bisecting segment. And asymmetrical hyperboloids would all have unique panels. So the imperative to reduce the number of panels also depends on whether or not we use symmetrical hyperboloids. And one of the bizarre things about this project is that we have this condition where we have to go from a purely straight vertical plumb line to these hyperboloid cylinder things that hold the stairs, which is kind of hard to do. And so the first thing we did, just in analog, was to produce a version that is composed out of hyperboloids. So we proved to ourselves that we could do it. And this would allow us to panelize it into flat planes, as I just described. And the next step is to reduce the number of panels. And we use a number of different techniques to accomplish that. So these usually we use standard angle increments, and we use repeating patterns of hyperboloids. The goal is to produce sequences that appear non-standard but actually are. And then we use those standardization techniques to make a version of the facade. So this version of the facade is purely repetitive. And you can see the isocurves. And you can see we have one unique hyperboloid for the stair, one asymmetrical hyperboloid that accomplishes the realignment, and then a series of identical ones that proliferate to the end. And we tried different scales of panelization. The next step is to make this flexible so we can adapt it to different conditions. So we generate all these scripts for connecting the different types of hyperboloids to each other. And when you put those together into networks, they generate these kind of complicated diagrams. So each one of these is a single set of surfaces into a global surface. And here you can see the construction of a surface as a series of scripts where we are adjusting the angle. So that looks like this. And essentially, the only way to do this is you take a guess. You get as close as you can manually by adjusting the variables. And then you run an optimization algorithm in Galapagos to find the final answer and lock it into place where it's purely vertical. And the reason you have to do that is that if you just run the optimization algorithm on all these variables to begin with, it'll think forever and never get close. But if you're very close and you can set the narrow range, you can find the perfect solution. So this is the first standardized facade made of pure repetition. And these are all the axes of the hyperboloids. And that version has 125 unique parts. And that's not the number of hyperboloids, that's the number of pieces. So individual panels that are mass produced and repeated to construct a facade. Those are the different surface types. And we can count because we know the approximate size of a panel, which is material dependent. And we know how many symmetrical and asymmetrical ones we have. Those are the asymmetrical ones. So there's another impulse acting on the facade, which is the fact that this project has a huge amount of mechanical. And the reason for that is that theaters need to be very quiet. And in order to move a lot of air, you either need huge ducts so the air can move slowly, or you need to move air quickly, which is noisy. And all of these ducts have to be on dampers and isolated. So actually we are using the ins and outs of the facade to hide and hold the ducts so that you don't see them when you're on the interior. So the facade, you can see here this version isn't working. The duct needs these vertical columns nested within it to house the ductwork. And it also needs to house the stairs because the stairs need to be on the perimeter of the project so that people can use them as egress. And in Columbia, you can have scissor stairs there to code there, which is wonderful. We just did that because we like scissor stairs and because a lot of people need to exit the building. So this is the facade in a state where it does not work. But the scripts that we have allow us to modulate this into various conditions with 4 variables on each hyperboloid. So the shear angle or angle of twist leads to the degree of twistiness of the surface. That's low shear angle, they're almost cylinders. Also the size or the radius of the hyperboloid, it's another variable. And the amount of exposure of the hyperboloid, it's another variable. As well as whether the isocurves are convergent or parallel. And we can use that to fit the mechanical, as you can see in this version. Again, this is a video of the optimization algorithm running. So back to this. And then we actually changed the hyperboloids that hold the stairs out for cylinders. And the reason we did this is because we decided, well, we argued about, Scott and I, because I wanted them to be hyperboloids, but then I became convinced he was right, that they need to be pure, cylinders, clear. They need to be all glass and true curvature. And you cannot have doubly curved glass affordably because there's only a few manufacturers in the world that can do doubly curved glass, and you have to, send it across an ocean. So typical curving of glass is performed by pressing the glass into rollers during the tempering process. And it's actually not all that complicated. And curved cylindrical glass is possible and affordable. So we replaced the cylinders with cylindrical glass. And that controls how many radiuses, the size of the radiuses and the size of the panels that you can have. And at this point, we are still discussing whether we would have one stair or two stairs, whether we would have a migrating stair and testing it. So all that stuff that at the beginning that was about rationalizing the particular stair, we weren't there yet. We were trying different versions of stairs and testing their effects on the outside, testing their effects on the inside. And eventually, we decided on these two equal stairs that Scott described to you philosophically from the beginning. One goes up, one goes down, they're ceremonial. So this version with the cylindrical clear stairs had 150 types of panels, so a bit more. And that's an image of that. So returning to the development of the facade, this version with asymmetrical stairs, 110 types. We tried one with cones, and that had 560 types due to the convergence. So it's interesting that the double curvature of the hyperboloids is actually more efficient, which is very satisfying.
Still out of control. Too many. Way.
And then we had this awful moment where the client said it looks too unstable. And so we did this thing where we aligned the axis of between the two hyperboloids along with the 45-degree angle. And actually, we ended up being okay with this because it's only on this moment that it preserves the stability and it actually locks the project into place. And then in other moments, it's unstable.
Carl, let me just tell them something about that.
Yes,
that was a
please.
Major crisis.
It was.
He looked at the model and he said he felt vertigo, that he would be afraid to be in the stair that tilts away from the building. And I was, oh my God, this was terrible.
Yes, I forgot that. That's true.
It was a very traumatic moment.
He felt like
we managed to convince him by working it out so convincingly with the engineer and breaking it into segments, making clear that the segments, each of them is plumb unto itself, and that are staggering outward.
That's why we built that model, right? The glowy model at the beginning.
He decided to stop worrying about it. It's just a matter of one having to accept something. But there was a period in which he was not so comfortable.
Yeah, it's true.
It's very interesting.
This one had 480 panels, so we're kind of getting out of the range of buildability here. And we created multiple versions with different degrees of twist. And the client selected this one. Actually, this one, it was a compromise amount of twist. And that we got down to 84 types of panels, and here you can see the types. Those are the 84 different identical panels. And those are the hyperboloids. And so at this point, we actually began to wonder whether or not the twist was having enough visual impact. And we evaluated this a lot. And we decided, because you can see each one is rather cylindrical at this point. And we decided that overall, the twist was still apparent. And we built this model. And you can see it. However, after SD, that was the end of SD. It was determined that 84 types was too much. And so we got it down to 33 for DD 25%. That is the last version of hyperboloids that we built. And you can see it down to 33 types of panels. And the entire back is a single series of identical panels. There's only 6 types on the whole back. Yeah, there you can see the different hyperboloids. And actually, this diagram shows the notion of clipping. So some materials allow you to clip panels after they're cast. and it depends on the material, whether or not that's affordable. So, you know, at this point, it really is important that we start to talk a little bit about materials. And we were considering 5 different materials at this point. So curved glass, flat panelized glass, doubly curved glass reinforced concrete, or GFRC, Creon, which is this weird material that's like stone, and metal, which is the low cost option. And each of those segments was produced as a mock-up. So these are the segments we created for the mock-up. Some are panelized into flat planes, and some are developable surfaces, and some are doubly curved, depending on the material. And here you can see the glass reinforced concrete being produced. GFRC can be doubly curved without significant additional cost if there are a limited number of types, because it means a limited number of molds. There it is being produced. That's the Creon, incredibly white. The client cared a lot about the whiteness. And here you can see the mock-ups being erected on the site, assembled, brought into with cranes. And so for a word about this, this is what's called a unitized facade system. This is a diagram by Arup. And basically a unitized facade system are a series of pieces that are built off-site and hoisted and anchored into place, as opposed to a stick-built system for like a curtain wall, which is usually erected on-site. And these units are typically secured, as you can see in this diagram, at the floor plates. This is the structure for this project. So typically the unitized panels would be secured to those floor plates. However, in our case, we have 2 conditions that don't allow that. First, we have these vertical atriums because the lobby is to be passively ventilated. This was an important part for meeting our environmental performance goals, and also, again, for limiting noise, so we don't need additional ductwork for the lobby. And also, we have migrating horizontal joints. They run on diagonals. So in both of those places, the unitized system cannot be linked to the floor plates, and we need this additional substructure, which you can see in this diagram. Also, this is a seismically active zone, so the joints have to have movement in 3 dimensions between each of the panels. And there's this complicated joint, which allows movement in all 3 axes. And each of the different mock-ups is built by a different manufacturer. So some of them actually developed custom details for the project, and not all of the manufacturers were able to account for the movement of the facade while preserving this migrating diagonal horizontals. Here you can see the glass and the concrete mock-up against each other. The interesting thing, though, is that the glass was a very innovative system. The manufacturer was developing something, and it was a sandwich of 3 types of glass, 2 transparent layers with an opaque layer in between. And the opaque layer is cut to allow for transparency. So this made the transparency independent of any structure or joint or mullion between the panels, which allows us to have windows without mullions like that. It's too beautiful to pass up. And so we decided that we had to go with all glass. And that, of course, means we can't build it out of hyperboloids. So all that work for nothing. We have to build it out of cylinders now.
I was right from the start.
Yes.
Cylinders were the answer from the get-go. The whole building became cylinders.
And so what we did actually is we analyzed, you can't see in these videos, but we analyzed the behavior of the facade as hyperboloids, and we tried to mimic that behavior in plan and section with a setup of cylinders, a specific way of linking cylinders together around this bisecting 2 planes that are mirrored around a bisector. And that actually creates an experience that is very similar to the experience of the twist. You can see that here, and it has the same types of controls that the hyperboloid did: radius, bisecting angle, and we set those up with a whole new set of grasshopper scripts, and we ran our optimization algorithm to achieve a version of the facade with 8 types, 8. So there they are. The maximum standardization we could achieve in glass, 8 pieces of glass fabricated and repeated to create the whole facade. And there are all the panels, 143 pieces in total. Some are solid, some have windows migrating across them. And I'm going to run through this quickly so we can get to the end. We also tried to deal with the canopy. You can see this canopy has all these mullions that are kind of, all the structure is kind of chaotic in this early diagram. And our goal was to align the canopy beams with the mullions to make that lift apparent of the lobby. And the canopy also has to be analyzed for drainage. So while the canopy is scripted, it's also evaluating the slope at every point. And these are the geometric rules that we have to use to link cylinders to each other. I don't have a video in this one, but you can see it's important to have a positive cylinder on the bottom of each of the positive cylinders of the facade to avoid some ugly clipping. We didn't want this canopy to trim the bottom of the facade. So and then we smoothed it in the negatives together, and we produced this condition where all the mullions of the lower glass align with the structural beams of the canopy, like that. And then each of these panels has to be split so that they fit onto the size of glass that the manufacturer can produce. And sometimes we need extra divisions and we have to hide those over the gutters. And this is the drawing we send out for pricing that shows all the different panels flatly unrolled. And now you can see the design again now that you understand it. That's the back. You can see the windows migrating across the horizontals. And the canopy is actually a rigid shape with the facade, so that relationship between them helps limit the structure in the model, in the site. And then the interior is a whole nother project, how to develop the theater. There's an interior view of the stairs. Another one. So since we are at our time, we can go very quickly. So the form of the theater is controlled by the acoustics and the sight lines. And actually every single seat needs to be looked at, sometimes subjectively. And we also had to try a variety of ceiling forms. The shape is very contested because you need a lot of volume. And so sometimes a transparent ceiling is desirable, but not visually desirable. You need a lot of volume for the acoustics. And these ceilings have to absorb the catwalks, and the location of the openings is controlled also a part of that. So we tried multiple versions of these. These are actually scripted as well. What we did in order, the ceiling actually can't touch the edge of the interior of the room because there's a curtain that goes past it to transform the theater from opera into regular theater. And so we had to make these odd transitions at the edge of the room, and those cannot be, those were a weird geometry, which then we replaced with approximated versions of trimmed cylinders to aid fabrication. And the balconies also rely on the same geometry as the facade, so they're planes that then are replaced with standardized cylinders. And they're trimmed at angles to preserve the sight lines. And we had to develop also the acoustical panels that can be stored, and that is the interior. So very similar project to the facade, happening over again. So to conclude, I'm going to turn it back over to Scott.
Oh, well, we really only intended to make a brief comment about the activation of the experience of architecture, how a project actually proceeds into life. And the experience that we've had has been this museum in Israel. But I think the most exciting moment in this has been that the space that we had thought was a dynamic and exciting and activated geometry, which, by the way, was the first of that kind that we kind of explored. It turns out to be the site because of the curator of a very different project, the curator who came after the initial client. The initial client, Moti Omer, unfortunately died. He was a wonderful client. Very tragically died right when it was finished. But a new curator came and really transformed the building. Go to the next slide, Carl, and you will see that artists were asked to intervene. Some of the art I'm not showing you here have really altered in unexpected ways, but the idea that the only point I wish to make was that I believe these kinds of spaces invite a different kind of response in certain kinds of cultural institutions. This is another dimension of this kind of work. They involve speculations and new types of activation of art and activity, potentially performance. I do think these will happen in remarkable ways also in the Bogota lobby and stairs as well. So anyway, we just wanted to toss that into the discussion as a conclusion. We see ourselves continuing in this. These are some of the projects that are incomplete, and the in-between of these dualities has to be much further explored, because as you can see from Tel Aviv, the inside is empty, and in Bogota, it's full, but we've never kind of occupied a dualistic interstitial condition. We haven't yet done that. That might be coming up. All right, so thank you, and we hope to answer any questions. As you can see, Carl's ready to jump in and get under the hood with you if you have any specific.
Scott, I just want to, and Carl, I thought that was a terrific expose into sort of the thought and the sort of the design research that you're invested in each project, right? And I've just really, for the last 20 years, you've been after this hyperboloid geometry, and you've found new ways to explore that geometry through a lot of your projects and a lot of your work. And I think that the breakthrough for me, and I said this in the introduction, but I want to re-articulate it, was I-beam. I really think the I-beam and not only the hyperboloids and then the circulation through them, but then the relationship of those to the structure and the tensegrity notion that you propelled in that project, I think has helped shape your entire work, in different ways. And this, I love seeing this, because this is a maniacal, version where you are really exploring the different possibilities of this geometry, its relationship to one another, and then taking us through the entire process of what it takes to get something like these contested geometries built, right? And it needs the same level of expertise and precision and careful thought, right? And some of these moments of these stairs that you showed from the interior is just spectacular, right? So I know you kind of start with these geometries, but you always test them through kind of the internalized movement and the atmospheres they create and the excitement of the spatiality, which you actually brought up right at the end as well with Tel Aviv, the Tel Aviv Museum. So I really appreciated the talk, and it's so important for students to understand that this work has such rigor to it. And it has so many moments of, you spoke of, moments that were really tough to deal with that the client put forward, but also then the solutions in such a restrained manner, restrained site, restrained poche, restrained geometry, restrained number of panels at the end, which were 8, I think, right? All of this develops this incredibly evocative project at the end. So I really want to thank you for sharing all the trials and tribulations that went into the work. And it's a fantastic way to start off the series. It's precisely what I need the students to understand. You know, it takes a lot of thinking and a lot of work to get to this sort of result.
I mean, I would love for Carl to try to describe what kind of state of mind he has to have to do this. I mean, I want to just say something, which is that the early work is about how geometry is put into tension from the conceptual, spatial point of view. And then in Tel Aviv, I would say it's a very primitive kind of construction. This is cast in place. Now, it was beautiful. The form work was very difficult to develop there, but it was roughly built ultimately, even though it was precise. In a way, it's rough on the surface because it's made of plywood patched together finally. Wow. But with Carl, things have changed significantly. He has raised this, I mean, it's like, maybe the word is fidelity. But to include, as you said, Ali, I love the way you narrated it, Ali, because you went through the numbers of ways it's constrained, you know, and concluded, of course, with the 8 panels. This is a very particular state of mind to sort of not indulge in too much freedom and to desire to push to limit points to reach high degrees of diversity and complexity within very difficult limits. And Carl loves to be acrobatic that way. I mean, this is absolutely essential to have this state of mind, to be willing to test it, throw it away and test it, torture oneself through all of that and still do it again another way.
Well, what I appreciate, you know, about you know, the working with Scott over the years, is that, you know, I don't totally feel very lucky that I entered into this structure that he somehow managed to set up, where we have the, you know, the time somehow miraculously to, you know, throw things away and really try things differently. And, you know, that creates an atmosphere where we constantly see each project as a continuation of the previous one. And where, you know, the joy of discovering something new whenever a wrench gets thrown into what we've done is allowed to flourish. So there's these moments where we have to sort of start again. And, you know, that it could be a problem, you know, in a different situation, but somehow in our practice, you know, we can view, and then, you know, the dialogue that, you know, we have in the office, that becomes like this joyous moment where we get to try a new project that we didn't get to develop, and we get to develop the fuel for a different project. So this moment of relinquishing some of the beauty of what you've done and trying a different version is something that he kind of taught me, I think, as a student and over the years working with him. And so that's something that I really value, because it makes that process wonderful.
Yeah. But the intensity, right? I mean, I think that I'm just thinking about, I mean, there's so much richness in a lot of the work here, but one thing that just really stands out is how you started rationalizing the hyperboloids originally, right? Through the cones, then through the cylinders, through the, you know, the different ways of coming up with thinking, even thinking through the problem of geometry and how one can build this with straight surfaces, right? And all those iterations that you went through to then develop, it also reflected back on the form, and it sort of made it tighter and made it stronger when you started actually having to reduce the number of panels that you could afford to build a project, right? So I just think that every step of this process has been fascinating to see for me. And I really appreciate the description, Carl. So, and I know, you know, it's not easy. And I don't think people, my students should think it is, right? it takes a lot of careful thought and a lot of intensity and a lot of desire to make it happen, right? Anyway, I think I've spoken enough. I want to open it up to questions. And I want to start, I want to ask a couple of students, perhaps Jason J, do you have any questions, or anyone in Beijing, do you have any questions for Scott or Carl?
Yeah,
Yeah. Oh, okay. You first.
You can go ahead.
Oh, okay. I would like to ask, in this project, you use hyperboloid cylinder, this kind of geometry controlling the form. So I would like to ask why you choose to use geometry, but not some free curve to organize the form. I would like to know how you're thinking about the control line in form generation.
Well, I mean, just to begin, we choose not. We don't have very much interest in a free form because we're interested in bringing these difficult and geometries into contact with the orthogonal world of architecture. There is a tension between these things that are breaking free from the orthogonal and the orthogonal. But there's also a desire to begin to make possible their rationalization so that they can be extruded as we are doing with the cylinders, or made of flat parts. They have to enter into the world of construction. Purely free forms are very indulgent and easy to make, but they don't allow this kind of communication with architecture and with the world of construction. The straight lines are essential. Those are the moments of truth. That's just where you bring it into relationship to the real world of architecture.
Right. And your work has always been about geometry. Geometry is always about lines, right, and curves.
Tanisha asks a question. He says, Scott, it seems like you knew the hyperboloids wouldn't work. Why didn't you stop Carl from going further with his idea? Carl!
I don't know how to answer that one.
Remind me, because I love it happening. Well, no, I have to tell you, I was very attracted to the hyperboloids because they are constitutively disciplined and regulated. I mean, it's thrilling, and I think we could use a fragment of one. I believe we're going to do something with them. I did realize at a certain point that since the stair was inevitably cylindrical in its segments, it seemed beautiful that they would just be broken by tilting giant cylinders. And I did understand then that we could just do the cylinders. But I wouldn't say I knew from the beginning I didn't want hyperboloids. He did go too far, but we always go. We always go way too far. We have done this with every project.
If you would like to ask a question, please put it in the chat.
We've gone way too far.
The discussion.
Many commitments that we end up not being able to.
You did know, though, you have a sneaking suspicion is what it is. You're like, I think that this is the destiny of this project is to become cylinders. And I'm like, no.
Well, I've been through that before. I would tell you one, the Goldman Sachs canopy, we pushed so far. We tried to make it out of hyperboloids, and we believed we could. And Harry Cobb, who was the principal architect of the tower and wanted us to do it, it was a project associated with that tower, pushed us to the limit to do it. And the client finally realized it was never going to work and fired me. This is pre-Carl days, literally. And I learned a lesson then that, we can do this in our own studio. We can go down the wrong path, be very excessive in our pursuits. But if you let someone see you do that and really do it, let's say, somewhat irresponsibly, I mean, irresponsibly insofar as it was just becoming more and more expensive and complicated. So I had to jump back and do something new and convince them to take me back. And they did. It became 3 triangles. The canopy went from being a complicated panelized hyperboloid to being 3 triangles. And it's very beautiful because they're manifest in a very precise, it's not easy what they are, They look simple, but it isn't, because they were made of ribs, and there is inherent complexity, but of a very, as Ali said, a very restrained kind. That's super restrained. This is still pretty ambitious to make this all out of different kinds of cylinders.
I wanted to add something to this notion of the free curve, because it is possible in today's day and age to, hire a firm, right, where you can build hundreds and hundreds of molds for individual and have thousands of individual panels. And with the BIM models that we have today, what usually happens is the contractor has a key for every single solitary panel, which is linked into the BIM model, which keeps track of them, and every key is linked to a mold. It's totally possible if you throw enough money at it. But it doesn't have a kind of an ethics given of expense. And I think we're interested in targeting this range in between, where these geometries are realizable without quite all of that expense. And also it can cause problems later on. For example, if you have to replace a piece of the facade, you have to go back to the original BIM model and find the original mold and, triangulate these things. And also you need to hire specific contractors to do that. So, and the contractors have to be on the hook for hundreds of thousands of extra dollars of insurance, because, they're responsible for building things within a millimeter of precision. So not everyone will agree to do that. So we're almost there, but it's not necessarily as interesting as trying to build, or as ethical as trying to build something that is standardizable.
Yeah, I just want to wrap this part of the discussion up. I think this is a big misunderstanding that a lot of students do have when they see anything that's curved. They think it's freeform. But your work is actually the opposite of that. It's coming off of geometries that are very buildable, and you clearly showed that. So I don't want to spend any more of our time there, but I have two questions on the screen which are similar in their sort of logic of questioning, which would be very interesting to hear about. As you move through the process and you develop a way of thinking about the project, is there any emerging condition that happens? Is it spatially altered, or or one of the questions is really about, is it just going through the process of making it, say, more buildable, right?
Well,
so the opportunity, I guess, is
yeah,
through the process, does something new come out that is super exciting for you, and then you push that? Or is it something that is just going through the process to allow it to become more rationalized?
Well, we just start with a slightly different way of addressing it. I mean, Carl, I'd like to hear Carl think about that. But I would say, for example, the original problem in Tel Aviv was a group of galleries that couldn't be reconciled with the site. It's a very different thing than to know that you have this giant theater. The theater, we're not saying enough about it, but it means you have a very different set of concerns in your mind while you're doing the work. I would say, for example, that in Michigan, and maybe Carl can speak to this, the question had so much more to do with the site than with any internal singularly defined program like galleries or a theater. It was really about the site. So I'm a little wary of saying that we just go through processes. Carl, I don't know how you would answer this. That each one begins with such a different set of questions. I don't think of it as altogether an exploration of process. Each one has its own problems and processes, each project, I mean, ultimately. But of course, we have an attitude, and you're right, Ali, it's inevitable that there's a tendency.
Yeah, I mean, actually, I have always found this fascinating. I don't totally understand it, to be honest, but Scott is not really fixed on a particular problem, absolutely, or on a particular way of producing work. It's constantly something that we find anew in each project. So I think the starting point for each project is never the same one. And sometimes we find ourselves questioning the same geometry, but usually not from the same angle. And that capacity to not reduce anything to a way of doing something, but still to have continuity and trajectory.
Yeah,
it's pretty.
But I think it's also important for the students to understand that design research practices, which you are, right? You do this design research that builds on itself. But that doesn't mean it's the same work, right? Each project explores new versions or new ideas within the confines of the project that you guys have been working on for a long time. So it's not like you're regurgitating older work. It's about producing new ways of thinking through the ideas that you have brought to the table through these contested geometries. And each project has a different way of dealing with it. And I think Scott answered that early on, right? Scott said, you know, Tel Aviv is different than Bogota, that's different than I-beam, that's really more about the, you know, integrity. So each step as it builds starts taking on different issues that complement a way of thinking about the project, but it also pushes your project of these hyperboloids forward into different ways of thinking. And I found the first series of models that you all built with the different stairs, you know, the ones you said that you would use maybe in a later project, you know, I found that fascinating because that was already saying, okay, this is interesting design research. We can't use it here, but it's going to emerge and, you know, come back somewhere else in our work. And I think that's really important to understand. I was presenting a project once, and one of my mentors just said to me, just keep doing that until you get it built, you know? Just keep doing that project over and over again. And it took me a while to understand that thought, but, you know, I think you have to just want it badly. And I think that that really propels the project as well.
They're asking me to answer some students the difference between this and like what ideas have come out, you know, compared to when the Tel Aviv was happening. And Carl, sometimes Carl, I remember we were looking at the synagogue recently. We were saying we've never done that thing, and I don't remember what it even is. We do constant narratives of what we're doing, and we will suddenly realize we've never done this before, whatever it is we're doing. So what was it about the synagogue? Whatever it is, Carl, I just said, I think that Bogota is pushing this innermost element, this stair with its own internal relationships of duality to the perimeter. It's not a facade, though. It's like the middle of Tel Aviv pushed out to the edge. Why does that interest us?
I mean, I can answer that a little bit. I mean, you know,
Yes.
I've been wanting to make an atrium like Tel Aviv ever since I got here, but we've not had a project for an atrium. And I think so there's something different about each project because I think, you know, this really, you know, speaks to the fact that it's architecture fundamentally that's motivating the project. You know, each project has a typology and architectural goals and realities. And, you know, Scott, I think you're mostly fixed on what's appropriate for the site and what's appropriate for the project. And that generates problems that are different for each one. So you know, I wanted to put an atrium in Bogota, but it has this giant theater and it generates different questions that have to be answered differently.
But Carl, I'm just trying to think about this whole idea. For example, in our newest project,
that wasn't good.
That's okay. We have a project where this building is utterly floating in the landscape. It's no longer forced into its position by the city.
Right.
Now, both Tel Aviv and Bogota were on sites, and Michigan, all three. Sorry,
right.
Michigan, Bogota, and Tel Aviv are on sites that were badly planned, misplanned. The master plan incorrectly conceived, did not anticipate even just.
Yeah, this was the thing you were talking about.
Yes. Now we have had many sites that were wrong for the building. And that is one of our great pleasures. We had I mean, long ago, I did a house. It started in 2007, didn't finally get built until 10 years later in California, where you could almost not build a house on that site. But this overcoming of the site has been one of the main motivations, but every time it is torturing the formal idea.
Do you remember what you said about the Kansas? Because you mentioned that we didn't have that in Kansas, right? It's free.
That's right.
So what do you do in the free site? And you were talking about Borromini. Is it? No, it's the Bernini, the ellipse that is caught with the door, right? So do you remember that one?
Yes, Stephen Kosovec just asked me, he's just said to me, what do you do when there is no pressure, when there isn't a determining factor of shaping the building? It has to come from within. Now, the theater is a form that's determined from within, but there is the outside that surrounds it that is determined by what's from the outside and from the inside in a very compressed way in this particular circumstance. None of that's going on in Tel Aviv. There's nothing really internally determined in Tel Aviv other than our own invention, which is the lightfall, which is actually a residual space between the rectangular galleries. Those are determined by just the demand that they be rectangles, but that's not nearly as predetermined as a theater or a sanctuary, which has sight lines and specific acoustical properties. And it's wonderful when you have an interior space that's highly deterministic. If you have a site that's highly deterministic, it's one or the other or both. What if you have neither? That's really troubling. We have problems with the idea of absolutely willful architecture. We like the fight. We like something to force things to have to be the way they are.
And I think I mean, yeah. I have a follow-up question for you, because one of the students who just wrote to me privately said, it's interesting that all your work is exactly this, is formally driven from the interior in this maniacal manner. How does it respond to the site? And I think that just from my reading is that you just explained it, sort of, it is kind of how you make best use of the site. And a lot of your sites seem to be quite restrained, right? Maybe the Taurus house, if I think about it, had no restraint.
Yeah. Carl, what were you going to say about isomorphism? We have this idea about form. But when yeah, Taurus house, wait, that's it. Ali is talking about, which is the unconstrained.
That's right.
But we had a name for it, which is isomorphism, which is when the inside and the outside are coincident, co-determined, Ali. So when you look at the Taurus house, it's just one form inside and out, and it's the opposite on either side. So when you pass through the void of a torus, you feel as if the other side is solid. And when you're in the other side, you think the middle is the solid. It's constantly flickering. There is no hierarchy, and it's a kind of duality of opposites. Figure is what Eisenman would call it. We are interested in this idea of singulars or isomorphisms that are very intensive. Why is that, Carl? Can you remind me?
Well, I think when the question of, you ask the question, what do you do when there's no interior pressure and no exterior pressure? But the pressure then becomes this one of isomorphism, which is Scott's word. It's not a real word. It means when the inside and the outside are coincident and the same. So the inside is fluid with the outside, like a house. It's made of furniture that is juggling around in a boundary, and you can flow in and out at any moment. It's the idea of isomorphism. And then, it's the tension between that condition of like housiness and the condition of big buildingness, where things start to differentiate themselves and become component parts. So nothing is either or. So there is always a tension between inside and outside, regardless of whether there's tension in the inside or tension in the outside. I think that's the main point.
How are you chaps doing? Can you take a
little more? We like it.
Okay.
How are you doing, Ali? If we tire you, Ali, You've
Oh,
been,
no, you can't time me out, Scott. You know that.
oh, you're a good
I'm
man.
always going to come back at you. So
You're a good guy. Well, someone is asking about the relationship to the old projective geometry and the new.
that's right.
Let me see what else. Hold on, let's look at some of these questions. Yo asks, I'm sorry, I can't see the full spelling of your name, Y-O, but you have asked, what is your standing choosing geometry when you are dealing with projects of different area? The geo has correspond with cultural context. Very interesting. Right now, actually, I'm working on a house where there's only one episode of geometry. It's the roof, naturally. I don't know if that helps answer the question, actually. I mean, so when you think about a theater, you know, it's the form of the seating and the balconies. The facade, we brought that to the project. We could have just had it be a box, the outside. I mean, that wasn't the desire of the client. They did wish for it to be something important and memorable in the city. But clearly the one form that could be, that was necessarily complex was the theater part. The reason Tel Aviv is complex is the site. And this house, well, this roof is going to do something absolutely extraordinary for the house, but it's very simple, but it has to do with bringing light and organizing the experience very unexpectedly, I hope. The perception of spaces that it creates, this certain form of the roof in a house. You could do something like that. Roofs are formed in houses. They move water. You know, roofs, they are the opportunity. We have this term, Carl, he and I, we say a project is roof dominant, or it's not. It's facade dominant. What does that mean? Facade dominant, that's Tel Aviv and that is Bogota, because in both cases, the facade is a highly activated part of the project and the roof is not. I mean, both in Tel Aviv and in Bogota, the roof is behind a parapet, basically. But we have some other projects where the roof is super active. Taiyuan Museum. In fact, the whole building is a roof. It's just a thickened roof. Some of you might have been to the Tel Aviv Museum. Carl came with me when it was under construction. He was my student then. It was 2000. What year was it, Carl? 2011, 10?
Something like that.
And
2010, I think.
He's in the picture in the construction shot on the website somewhere, I think.
Yes.
But anyway,
right.
imagine it's a very complicated roof, which is both landscape and roof, and it's been extruded. That's such a different kind of project, the Taiyuan Museum. You all are in China.
You're talking about, I mean, the question is about culture, but you brought it back to the discipline. I think that's pretty interesting. I mean, that's how you define it. You define
the program. Maybe Ali, maybe
the discipline.
I'm not sure it's the discipline, but it's the program. In other words, I think
the
that
roof or the facade or the corner or
okay, yes. Oh, I see what you mean.
To
you're
the
right.
volume or the
Sorry, you're right.
around, right?
Yes, to an architectonic origin. Yes, disciplinarily. You're right, Ali. I'm sorry. But I think, Ali, what I'm saying is each of those is aligned with a programmatic and cultural condition.
Right.
So in the landscape project, maybe it's the roof and the ground. I mean, that sounds very literal, but it's true. In a house, the roof. For many reasons, the roof is more significantly the territory for geometry.
I think, Scott, though, that once you're a student, how does this get translated into cultural context? How do and for me, it started to make sense when I actually think that there's a way that we talk about it when we talk to each other that is not actually the way we translate it into reality. And I think that in reality, it's about respect. So there's actually an idea that these sorts of narratives and these sorts of geometries have real world effects that are experienced by the people on the site, and that those effects are elaborate and complicated and interesting to the mind. And so there's a respect of the viewer and of the person inhabiting the project that is embodied in the idea of bringing the elevated geometry to the context. So when we talk about these elaborate narratives of form and why it looks like this and what is this particular narrative and how it bends this way, we believe that those have real impacts on the ground and that those impacts are respectful of the client and the person that inhabits the building. And I think that is the connection.
I'm answering. I'm answering the question of Yu Yishi. Yu Yishi was asking about the geometry projective versus this later work, Carl. And I don't think the matter of it being hand drawn or not is really of importance. The issue were the ideas of projective geometry, which had to do with the perceptions of the anamorphic, which, as you know, is a kind of peripheral view of the frontal, of the way we see things in perspective and time, the implication that something is distorted by our vision or by the circumstances that distort it. You know, a building is distorted because it can't be what it wants to be. It got into a bad site and it couldn't be perfect. That's one kind of distortion. Another is the kind that's like enthesis in the classical, where something is distorted so that it looks more correct to the eye. Different. And this is what I wrote about for Ali. Ali inspired me, I have to tell you all, to do an essay, which I don't usually respond to requests to write anything. But he had this idea about elegance, and he defined elegance in a way I'd never heard it defined before. And I thought, I've got to write about this. I knew this was going to be significant. Carl will tell you, I have a witness here that I don't write unless I'm absolutely nailed to the wall, because it's very painful. And I know it's going to be a huge investment. It will take very long for me to write. That essay took forever, Ali. You owe me a ton for that essay still. He made me write an essay.
13 years ago, Scott.
You still owe me. It's called Attenuation, the essay. It's about stretching, you know, the elegance of what is attenuated. But anyway, what I wanted to say is it's about distortion. And the projective geometry was always about manifestations of that in a very disciplined way, to use your word, Ali, the techniques that make something disciplined. And so it can be digital or hand. Of course, when it was hand, it was painful. It was laborious in a different way. It was very limiting, very slow. That's not reasonable. I wouldn't continue with that. But that's okay. It's all there. I mean, I think I told Carl, I just said that the voids of the lightfall are lines. And they're oblique lines that have been extruded into planes, which is true. That's what they are by definition. It's still the same inherent idea. Okay, let's see what Carl says. Projective is also an answer to the question of how do we find a common language like the classical. You have asked that question for years, and that was one particular answer, the projective. Yes, Carl is right. I was looking for a way to extend the language of architecture in some reasonable, rationalizable way. Oh.
All right, guys. I mean, this has been absolutely fantastic.
Too much. We had too much to talk to you about.
Much more. I remember the old days, Scott, when you used to come by to my seminar and just go off.
Oh, no.
Remember those conversations we had?
Yeah, we had some good ones and arguments. You and I have argued.
Right. We used to argue.
Ali has had great reviews at Penn, and I did come to many. They were about the towers for a while that he was doing. Some of you might know about that period when he was investigating the slender towers. Did the students know about that, Ali?
They must know about it, but they weren't involved. Yeah, they must see the work from prior.
That was a great experience to see those over the years. I came 3 times, I think, didn't I? Something like that.
And at the end, we sort of built all the 7 megatowers, which are actually now going up, which seems so absurd how the economy of New York has changed drastically.
Now, what are you doing right now in a sentence or two, Ali? What are you doing with this group right now?
We are working on a UPS headquarter facility in West Soho, which kind of combines office with logistics. It's quite interesting to develop a new way of thinking, not only about the combination of different sort of materials together, but also really just exploring what the future is going to look like in all office buildings, right? They're all
Oh.
being taken over through logistics and Amazon and all of these delivery systems. They're going to be more integrated into buildings in the future. So we're looking into those sorts of issues this semester.
And you're reflecting, I suppose, or projecting a post-COVID reality.
Well, I don't want.
What are you doing with that?
Some way, but not so. It takes me a while to kind of think through these issues, and I don't want to be sort of just responsive or have a knee-jerk reaction to what's going on currently. But yes, eventually we will figure out the ramifications. It may not be this term, but it will be next year, or when you reflect on it and can really develop it into a project. I think that would be interesting, right? But there's not only COVID, there's also a lot of other issues that are at stake currently, right? And I think that that's important to understand, is that once again, I think that it's a program. So there are a lot of other classes and seminars that they have to study. And a lot of these issues are taken up in different classes. So it's sort of a holistic way of thinking about an education for an advanced design degree, right? So this is the first year actually where we have 3 semesters of a curriculum, which is separate than the MArch curriculum. It doesn't repeat it in any way. So I find that fascinating. That's an interesting project for, for a few years to sort of test where these seminars should feed into studio and how it should develop. But I think that the students are becoming really excellent in not only ways of making, but also in thinking and conceptualizing things in a much more direct manner than when you could only focus a studio on a topic. So I think it's actually fascinating, Scott. You should come through. Look at the progression of the work. It'd be lovely to have you. So let's just wrap up and say thank you very much. And we're all very appreciative of your and Carl's time. And that was really indeed an expert topic, an expert discussion and description. And we're trying to build experts in the future. So it's really important for them to see what it takes to get there. So thanks a lot, both of you.
I just want to say the responses have been so wonderful. And I just wrote a note to everybody, but this is a great group. You must be inspiring them because everyone is so engaged and asking so much. I love the willingness to be forward with your thoughts and questions, more so than I hate to say it, than the students at Harvard. I don't find them quite as forthcoming with questions as you have been today. What do you think, Carl? It's wonderful, isn't it?
No, it's totally wonderful. And I really appreciated the way that you were able to take some of the things that Scott and I say and kind of bring them into a conversation in a language that makes a little more sense and can weave between the different themes. So I really appreciated that. Thank you.
Yeah, like Ali, that point you made about the discipline, and I hadn't seen it. I mean, those kinds of clarifications. These are the kind of conversations where we can, what he saw as discipline and I was mistaking as a matter of programmatic identity, and I really wasn't right. So these moments where we discuss with each other and clarify thoughts are key, and that's what makes a seminar like this so constructive, and focusing on single buildings, Ali, was such a great idea. It allows you to really do that.
Yeah, well, thank you.
It was a lot of fun.
Thanks a lot, guys.
Thank you. Really inspiring to get to be around this.
No, I think the students are super inspired. Everything I'm getting in private, they're very excited. So thank you very much for your time, guys. And hopefully,
all right, I'm reading everybody's thanks. Thank you.
Come by our review, guys. Come look at the work. Let's keep discussing architecture. It's always a pleasure with you, Scott.
We will do it. Okay.
Oh, great.
Thank you. Thank you so much. Really, thank you.
Bye, everybody.
Bye.
Thank you. I see all your thank yous. Thank you.
Bye-bye.
Very nice.
Bye.
Bye.